We talked about acid solutions, so now we'll talk about base solutions. A strong base is one that dissociates completely in solution. This definition is very similar to the definition of a strong acid. Strong here means they're strong electrolytes, they ionize or dissociate completely. So for a strong base, the hydroxide ion concentration will be equal to the concentration of the base. Here's a table of some strong bases. Most of these, most strong bases are either going to be group 1A or group 2A metals with hydroxide. The group 1A metal hydroxides are nice because those metal ions are highly soluble, and so you can get concentrated base solutions. The group 2A metal hydroxides, like strontium and calcium, they are only slightly soluble, but they do produce 2 moles of hydroxide ion for each mole of base. Unlike the diprotic acids, which lose a proton in one step and then lose another proton in another step, because these are already ionic compounds, they just dissociate completely in one step. The soluble part, that is. A weak base is a little bit like a weak acid. Most of the common weak bases will produce hydroxide ion, which is the definition of a base, by accepting a proton from water. So here we can use B as a stand-in for weak base. So the weak base will interact with water and take that proton, that hydrogen ion, from the water, resulting in the production of hydroxide. So the weak base doesn't actually have hydroxide in it, like the strong bases do, but it still creates hydroxide ions. So ammonia is the most common weak base that we will see, and so ammonia reacts with water to form the ammonium ion and hydroxide ion. And again, these are equilibria. They are not complete reactions. So we talked about the acid dissociation constant to identify the strength of a weak acid. So we're going to use the base ionization constant for weak bases. So Kb, equilibrium constant. So the base reacting with water to form this conjugate acid and hydroxide. So here the equilibrium constant expression would be that concentration of the conjugate acid times the concentration of hydroxide divided by the concentration of the base. Water, being a liquid, does not come into these calculations. So if we have a smaller Kb, that means we have a weaker base. Because if Kb is smaller, that means the concentrations of the products are smaller. The reaction does not go as far in the forward direction, and so the base is weaker. We can also take the negative log of Kb and call that pKb, just like we did for pKa. There are a lot more weak bases than strong bases. Here are some of them, and here are the Kb values. There's a much more extensive table in the appendix at the back of the book. Many of these are forms of ammonia, basically. Yeah. So here's ammonia, right? And ammonia has a nitrogen with a lone pair of electrons. And so it can take the hydrogen ion and form the ammonium ion, leaving the hydroxide ion. Other wake bases are amines, which are basically substituted ammonia. So here is the nitrogen with the 2 hydrogens, but instead of a third hydrogen over here, it has a methyl group, or it could have an ethyl group, or any number of organic substituents over there. But we still have the nitrogen with a lone pair. And so it can still take a hydrogen from water and create hydroxide ion. And so then we're getting an extra hydrogen on that nitrogen, and we'll get a positive charge. So going back to these guys, here we've got carbons and hydrogens and a nitrogen. There's the nitrogen, 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 nitrogen. So those are going to be weak bases. I don't expect you to know their names, except for ammonia, but try to recognize that those are weak bases. The other two weak bases in here are quite different. We've got carbonate ion and hydrogen carbonate ion. So those are also weak bases. So when we have strong bases, the contribution from the autoionization of water is negligible, and so we can just find the hydroxide ion concentration is equal to the concentration of the rewind. Okay, start this one again. So with strong bases, the autoionization of water is negligible. If we're trying to find concentrations of hydroxide or pH for a weak base, we're going to do something similar to what we did for weak acid. We're also going to neglect the contribution of the autoionization of water. We're going to make an ice table, and then we're going to use the Kb expression to find the hydroxide ion concentration. So here we have barium hydroxide. Is that a strong base or a weak base? That's going to be a strong base. So finding the concentration and pH here is easier than for a weak base. We do need to be a little bit careful, though. So when this dissociates, what do we get? We get a barium ion and 2 hydroxide ions, right? So if we have a 0.010 moles per liter barium hydroxide, and we want to know the hydroxide ion concentration, we could think of this in terms of stoichiometry. We're going to get 2 hydroxides for every one of these, or 2 moles of those for every one of those. So 2 moles of hydroxide for every 1 mole of barium hydroxide. And the units cancel out, and we get a hydroxide ion concentration of 0.020. Or you may be able to look at this and just, your brain processes, oh, the hydroxide ion concentration is twice as large. That's great. Other brains kind of overthink things and say, well, was I supposed to multiply by 2 or divide by 2? I can't remember. And so this is how you can prove to yourself, using units, what you're supposed to do. So that would be our hydroxide ion concentration. How do we find the pH? There's actually 2 ways we could do it. Remember the circle of pH? So we could take hydroxide ion concentration and calculate POH, and then get to pH. Or we could go to the hydronium ion concentration and then go to pH. Either way. I think going through POH is easier. So let's find the POH of this. POH is going to be the negative log of 0.020. 1.69897, and then it goes to some zeros. How many significant figures do we have in our concentration? 2. So what does that tell us about this POH? 2 decimal places, right? So we would cut it off there. So the pH then is equal to exactly 14 minus our POH. Press the wrong button. So 12.30103, again 2 decimal places, so the pH is 12.3. And that's our other, there's 2 answers here. Any questions? Giving you one of these group 2A metal hydroxides on an exam to calculate the pH or something is one of my favorite things. I don't think it's a trick, but students mess it up more than like sodium hydroxide. It's a little more challenging. So just be aware of that. Watch out for that. Okay, let's do a weak base. So here we're asked again, hydroxide ion concentration pH of methylamine solution of 0.33 molar. We're given the Kb. The fact that we have a Kb suggests that it's a weak base. We also have this title up here giving it away. Do we need to know what the formula for methylamine is? No, we don't. We just need to know it's a weak base. We can just call it B. B for base, right? So the base is going to react with water, and it's going to form BH plus hydroxide ion. And so we can make our ice table. So the initial concentration of the base is the 0.33, 0.33 molar. What's the initial concentration of BH plus? 0. And how about OH minus? About 0, approximately 0. That's... I just went a little too far there. That's a 0, right? And then what are the changes? How does B change in terms of X? It's going to lose X, right? And how about BH plus? We'll gain X. And OH minus? We'll also gain X. So then we add the initial and the change columns, rows. And then the Kb expression is concentration of BH plus times the concentration of hydroxide ion divided by the concentration of the base. So we get X squared over 0.33 minus X, and that is equal to the Kb that was given to us in the question. This is one where the X is small approximation would probably work. And so if we do X is small, then that X goes to 0. And then we end up with X being equal to the square root of 0.33 times 4.4 times 10 to the minus 4. Zero point 0.1205. How can we tell if it was appropriate to use the x is small approximation? We'll take our x and we'll divide by the number we were subtracting it from, the 0.33. I still got that number in my calculator, so I just go divide by 0.33 times 100, 3.7%. Smaller than 5%, so that's okay. Get people to stop texting me here. So are we done? No, we're not. We found x, right? But then, so what is x? It's the hydroxide ion concentration, right? So the hydroxide ion concentration is equal to 0.012 molar. But we need the pH. So we can calculate the pH from the pOH. So pOH would be negative log of 0.012. I'm going to go ahead and throw in the 0.5. And that gives me pOH equals 1.9190. And then the pH is 14 minus that. .08. Yes. Where the 14 comes from? Yes. So in the circle of pH, we looked at all those relationships. The relationship between pH and pOH is that the sum of pH and pOH equals 14. That 14 is from Kw, which is 1 times 10 to the minus 14. So when we're taking the logs, then we're finding the power of 10 that those concentrations are. And so just like hydrogen ion times hydroxide ion has to equal this, pH plus pOH has to be 14. Good question. Anybody else?